No problem. Okay, so I think I have slide a lot sheets as you we saw when I sent a presentation yesterday. I think I think we have two blocks of 90 minutes. Is it right?
Yeah, it's nice.
Okay, so I think we start and then make a break around 11 because then I have to change from my hotel room to the lobby. But I hope everything works. Please give me feedback if there is something with the technique not working right. Yeah.
Yes, of course, of course.
Okay. And I don't know how you made it usually. Do you put the questions you have directly, or you make it afterwards, or you may put it in the chat? What is the way you prefer?
We usually, if we have a question, we ask it because otherwise you forgot it and some. So if
Okay,
we stay
great.
with you, it's. But this class is all quite silent, can I tell you? So it's usually most I that ask the question, but
Okay, good.
I
So
encourage them to ask the question. So
let me see that I can start the presentation. Um, do you see now the presentation?
yes, I don't. I have to.
Okay,
Yeah, yeah. Thank you.
great. Then let me. Okay, how can get one here? Okay. Okay, basic of filling. I don't know what is your background right now. How much do you know about filling? Are you working in, I think you're rather in small breweries, yeah?
Yes,
Okay.
we have. I can tell you that we have studied for 1 year, and they have made their what do you call it in English? LIA. They have been on a brewery for 10 weeks this spring, and they're going out again to breweries internship. Yeah, bra Martin. So they have
Okay.
yeah. So they have different kind of. It depends because they are really small breweries, but some have been really on a packing hall and so on. So it's quite different.
I understand.
Yeah.
Okay, I understand. Okay, so I think we have now some minutes to have an overview about filling and canning. To be honest, I know that usually a brewer is not so much into filling and packaging. Yeah, the thing where your heart is burning is a brew house, and usually for a brewer, the brewery starts with a brew house and ends with a brew house. However, why filling and packaging might be relevant, it's always there's a good introduction to see here. There's a Kronenburg brewery in French, Strasbourg. I don't know, I think it's a quite known brewery, and this is like the wheel from up. And when you see, this is brewing and fermentation, so the heart of the brewery. However, if you compare it to fillet and packaging, fillet and packaging is a much bigger thing, yeah. So actually, the equipment is much more expensive, and as you see, it's a bigger part of the brewery. So this is maybe some indication why it might be also relevant. Also, what we always say to make it more interesting, the filling and packaging for the brewer, the filling and packaging is the part where you can screw the beer, where you can make a perfect brew from the brew house to a disgusting product. And this is, of course, something you should prevent. And this is why filling and packaging is also very relevant. Okay, just some introduction, some word. What is packaging? We have some definitions. So first of all, what is the function of packaging? Of course, the main point is that we have something to put the beverage in. Yeah, something which is giving the closes the beverage. This is the main function. But however, we have also some other very important functions of packaging. For example, information, like legal informations. What are the ingredients? I don't know, like the ABV, the alcohol, and some other, maybe even some things like which are relevant for allergy and so on. This is also something which is very important, a very important function of the packaging. I don't know, even some other like gimmicks, some advertisement things. For example, I have that cans of here Coors Light American beer, where that mountain turns blue when it's cold to drink. If it's not cold, it is white. So you can even make some fun and some advertisement with the packaging. So some other definitions, the packaging mean is that the package itself, for example, a bottle, a can, a keg, so a cask, but also some secondary closures, which are not really have the product contact, such for example, as a crate or cardboard boxes for six-pack trays and so on. This is the packaging mean. And the packaging material is, of course, the material of what the packaging mean was manufactured. For example, when we're talking about bottles, it's glass, cans, metal, and so on and so on. And then we have also some packaging aid things, which, for example, are labels or the glues which are used to put the label on the beverage. Okay, I think I don't know how it is in Sweden, but I think more or less in Europe it is the most important, the most dominant form is glass bottle, the returnable glass bottle for beer. I don't know if it is now, but maybe it will also change within the next years. This is like a study from 2018, where said like around 50% of the bottled beer of the bottled beer is sold in returnable bottles. But this is differs significantly by the market. So even in Europe, Western Europe, for example, he says like we have 62% of the sales in Netherlands, for example, are in returnable bottles, while in UK it was close to zero. However, I don't know what about the Green Deal, if it's also like a thing for you in Sweden, like something like which the governments were saying that to transform more and more everything into returnable packages. So this is why it might be, even if it's not now a big thing for you, glass bottles, returnable glass bottles could be something very, very important for the future. Yeah, some advantages and disadvantages for glass bottles. Somehow the mechanical stability that is important compared to cans. We will see later with the filling technique. Purity and mechanical lifetime. A glass bottle, of course, if it's treated well, can be filled up to 50 times. Can be even nowadays you find in the German market some bottles from the 1960s, so they are quite stable. No permeability for gases or other substances. This is important. So, for example, no oxygen can come through the glass and no CO2 can go out of the glass. However, there is some gas transfer, but this is mostly due to the lid because there could be something. Inert, this is the same, like high hygienic quality, we can wash it quite well. Transparency is a good and a bad thing. We will talk about that later. Reusable, also recycling possible if you're not, if we are not refill them directly, they also be able to recycle. They are cheap and can made usually with the domestic raw materials. However, they are heavy. They can break. When something is very brittle, of course, it's hard. Then we have a thermal shock, thermal sensitive. If we, especially later when we're cleaning and filling the bottle, we should avoid big temperature gaps. And also transparency, which is here something which is good to see the product, but also could be bad, we'll see later on. So just, I don't want to now talk about a lot of the manufacturing or the components of the glass, but for example, just as an information, most of it, like 2/3 or 3/4, is a quartzite, so silicium oxide. Then we have some other things such as sodium carbonate to reduce melting temperature while manufacturing, and something like limestone to increase stability and durability. For the colors, we could use for brown glass, for example, some iron and sulfur, green, some chromium oxide, and some cobalt for blue. Here, yes, I don't know if you're interested in. Here are then the compositions of what is a glass bottle in weight percent, and as you see, most of that is at quartz and silicium oxide. Just quickly to the manufacturing of glass bottles. Basically, there are two main ways to manufacture a glass bottle. The first one is a blow. Is a more older one process. The blow process means I have the liquid glass bulb goes into that mold in that form, and then it is blown from the upside to have already like a pre-shape. Then that mold is turned, and then afterwards it is blown from the top that the bottle gets its ready shape. Yeah. So very simplified says, I don't want to go now here deeply. Actually, I'm not an expert in manufacturing glass, but this is a blow process, and then more modern is a narrow neck press and blow. Actually, it's more or less the same, but in the first step where the mold is upside down and in the blow it was blown, here it is mechanically put into the form by means of something like a stamp. So that I press it inside with a mechanical thing, not by air, and then the rest of the process is the same. I turn it around and then blow it to the original shape. The main advantage of that narrow neck press and blow is that I have here in this part a much more even glass distribution. As you see here, there are some like gradients in that thickness of the glass, and this is then more likely to break. Yeah, and with this narrow neck press and blow thing, I can in the end have a smaller, thinner glass, and then have some kind of light weighting, so material optimization, and so this is something which was very important within the past years. But the glass bottle is not only a glass bottle. We have there some other things on it, and very important is the hot end coating and the cold end coating. Actually, the hot end and cold end coating, the name is because of the container temperature while manufacturing them. And the hot end coating, the container temperature has still a temperature of 500 to 700 centigrade. And the hot glass surface is something vaporized with the fog of a metal. For example, a tin coating or some titanium tetrachloride coating. And this reduces the reactivity of the head glass surfaces by creating a metal oxide layer. The thickness could be between 1 nanometer and 1 micrometer. Excessive coating is not very good, can cause corrosion of crowns. I have a slide for this later. And this hot end coating, first of all, it prevents already the growth of micro cracks on the outside of the bottle. So the stability, for example, the internal pressure resistance of the glass bottle is increased to that metal coating. And also it is a adhesion basis for then the cold end coating. Yeah. And the cold end coating, you see here that video where the bottles and they are sprayed with that coating material. The cold end coating has some thickness of somehow 10 nanometers, and this is now some plastics, for example, PP or PE. And this is first of all saturation that reacts with the metal oxide layer from the hot end coating. And this is important to create a smooth, low friction surface that I have less friction on the bottle line, so that then the bottles are moving within each other. There's less friction, and therefore I have that scuffing in returnable bottles, as you see here, is then reduced or slowed down. Yeah. If I wash the bottle, I don't know, 5 to 10 times, there is no cold end coating there anymore. Then I have a rapid increase in that scuffing. But in the beginning, first of all, also very important then for non-returnable one-way bottles, I have that that smooth area so that the bottle looks new and shiny. So transparency of glass bottles. This was where we were already talking about, as it's from one time it's positive to have a view to the product. From the other side, there are wavelengths in a specific range here between 350 and 520 nanometers, and that can cause like a reaction with the hop components and produce that MBT, 3-methyl-2-butene-1-thiol. And this is what we all know as the light flavor, the skunk flavor in beer. Yeah. And this is usually undesirable by most consumers, and it's a very low threshold. And this is very something which you can then reduce by the bottles of the color of the beer bottle. So if you see here, the amber, the brown glass bottle, does not let any light wavelengths through here inside the bottle, so that will not happen. But other things, such as white or green bottles, will then cause that reaction, or will allow to cause that reaction. Brown bottles offer the highest protections, green bottles offer low protections, and transparent bottles will offer almost no protections. So if you now ask yourself, why is it still possible that there are green and white bottles there? First of all, if you are not in Germany, if you're outside of Germany, you are not committed to the German purity law, so you can use special hops which are preventing to some extent that reaction. And first of all, this is of course only possible if you have your own bottles, if you don't use pool bottles, that you can put some UV blockers in the bottles to prevent that. Yeah. But if you have a pool bottle, like, I don't know, that returnable bottles every brewery uses, of course, you should not use white bottles. Okay.
It's interesting. Can I ask you? It's interesting.
Yeah,
why don't you can you make a bottle that's completely black that you can't see anything inside? Why don't you do that? Do you understand?
Well, I think maybe the coloring, for example, for brown was some iron. I think is maybe easy available and cheap, and I think maybe it even exists that it's completely black, but I think it's then for this case it's not necessary. But I think, of course, if you want to see it for marketing thing and so on, I can imagine a bottle completely black. Yeah, but I think the brown is totally sufficient to reduce this reaction, and then it's easily available. We have a lot of brown bottles, and if you then start now with a black bottle, it would be also then just for your brewery. But I don't know, for marketing, maybe go for it. Okay, then just one word to the bottle design. We need a minimum headspace, so a minimum brim full volume for pasteurization. So if you pasteurize the bottle, you of course have a expansion of the well volume because you're heating the liquid, and then there is a volume, and this needs some space. And there is this rule that for every 10 Kelvin temperature increase for every 10 Kelvin temperature increase, 0.6% of the container volume is needed as a headspace, even just for letting the increasement of the bottle some space. So if you now make just some jumps and some calculations, filling temperature of 10 degrees, pasteurization at 60 centigrades with a 500 milliliter bottle with quite standard values. Then according to that rule of thumb, you would have a 3% of expansion, so you would need a 15.6 milliliter of headspace to avoid some bottle explosions, bottle cracks. And this is why usually a 0.5-liter beer bottle, in this case a long neck bottle, has always like 520 milliliters of brimful volumes. For example, with bottles for juice, which needs much higher pasteurization temperature, you would then have a much bigger headspace. For example, 530, 540. Okay, filling lines for returnable and one-way glass bottles. We start now very basic with a layout. With a layout, and here is an example how that could look like. I think we will maybe start now to take the way of the bottles or whatever the crates in the filling line and see what's happening. First step is the depalletizer. So imagine we have a pallet with crates of dirty, empty beer bottles going inside the bottle line, like a forklifter or whatever, puts that pallet into the filling line. And the first machine then would be the depalletizer, is basically like a robot, which is taking the crates layer by layer from the pallet here then on the conveyor belt for the crates. The pallet is then empty, it goes here, then here's something like a pallet inspection if they're still intact, and then goes to the next machine, then or the last machine with the palletizer, and thereafter the filling process will get the new crates, but this we see later. Okay, then we have here the way of the crates with the empty bottles go to that to the conveyors and then entering the unpacking machine. Unpacking machine means I have a machine, it's also like a robot with grippers who grips the beer bottles out of the crate and puts them here, the empty bottles here on that conveyor. The empty crate goes to the crate cleaning machine, to the crate washer, and then to the packing machine, which is basically the same, but vice versa of the unpacking machine, where then later the full bottles are put in the crates. But let's focus on the bottles. The bottles here go then in the bulk transport to the bottle cleaning machine. Bottle cleaning machine, first big machine. Usually, if you don't have a pasteurizer, they are the biggest machines. Also, they are like consist of a lot of steel, so are also very expensive machines. So, but the bottles go into the bottle cleaning machine, then get cleaned, and then later on are leaving that machine. In this case, it's the same site. And then this is here very important. The bottles goes from bulk transport into single file transport, that all bottles are just separately. And then it's a very important machine, the empty bottle inspection machine, which is checking if the bottle is clean, is it the right bottle and without any objects, for example, glass splinters or whatever. Then, of course, the most important thing afterwards, the filling machine, which is usually blocked with a clothing machine, and then the filled beer bottles closed, then go from single transport again to bulk transport, and then entering here the tunnel pasteurizer to have some heat treatment for microbiological stability, and afterwards go to the label machine, where they got the labels, and then in the end, entering here the packaging machine, where they get into the crates, and then the full crates go to the palletizer, and the pallets are stacked on the little crates are stacked, and then here leaving the machine. So, and I will now talk a bit more more precise about those some of those machines. Okay, let's just start now with the transport. This is like usually what you're having, like that transportations of the bottles. I don't think that I have to go now in detail. You have that conveyor chains. And then, of course, you need an engine here, a motor, and so on. You have that sidewalls, that gears, which are holding the bottles for the right position. Very important, what you cannot see here, usually you have also some belt lubrication, that you put some chemicals and water on those conveyors to have also like a frictionless transportation of the bottle. Yes. So I already said, like, there in that thing that we have a lot of things where the bottles are going in bulk transport, and also some the parts of the machine where the bottles are going in single file transport. For example, they're entering the washing machine in the bulk transport, but then for the inspection machine, for the filling machine, they need to be in single file. And it's nowadays standard that you have like the separation, or here's a separation process, like pressure free. Yes, with that, I don't know, Kronis called it glide liner. The other words have other words for that thing. And you see here that we have the bottles, of course, when they are in bulk transport, you need less speed of the conveyors to have the same amount of bottles than when it's single. So you see here, I have increasing velocities of those conveyors, and this is how I can achieve then that pressure free single file transport. Here it's like the other way around. I go from single to bulk transport, and I slow down the velocity, and therefore I have that smooth pressureless bulk transport of the bottles. Here also, this was now, of course, standard big breweries, but here you see how it could be also made very good in a smaller brewery, how it's solved, that I have here that separation, that I have that even we don't have, even I have that 90-degree shape there. I can work when I have the right steer, the right program here of those velocities. I have here like that pressure-free, smooth separation of the bottles. Okay, now something about some efficiency and also some output and so on. If I have the filling machine, so the filling machine is determining the output of the filling line. Yeah. If I have a filling machine, which, for example, fills 20,000 bottles per hour, I mean the filling line produces 20,000 bottles per hour. So we already talked about shortly about all those machines. If these machines would run without a stop and all with the same speed, the full filling line would be full of bottles. So if I now have a stop at one machine, there are a lot of things turning, there's always some interference, there's always some stop. If I now would have a stop at the depalletizer, and we are assuming that every machine runs with the same speed, and the machine is full of bottles, that stop afterwards, of course, will then go to the unpacking machine. Afterwards, I would have that gap of bottles at the bottle cleaning machine, at the empty bottling machine, and then at the filling machine. And if I have a gap of bottles at the filling machine, then of course I will not be able to fill my 20,000 bottles per hour. This is why the efficiency of the filling line is going down. Yeah. Afterwards, the stop then, or this gap, is going to the other machines. So this is why you are having the output of your filling line according to that V diagram, also called Berg diagram. The filling line is a leading machine. which runs with a nominal speed, in our example, 20,000 hours per bottle, 20,000 bottles per hour. And then all machines, upstream machines or downstream machines, run with a higher nominal output, like up to 150%, between 130 and 150%, for example, at the depelletizer. And through that now extra higher output, now we have that same example. I have that there's that stop at the depelletizer, so I don't have produce bottles at the depelletizer. But due to that higher output, I can, with each machine, I can reduce that gap of bottles, and in the end, the filling machine will not see anything of that stop, because all machines are working faster. And this why I still be able to fill with my 20,000 bottles per hour, and therefore I don't have a stop, and my efficiency is not going down. So this is like a very basic way of filling lines, how they produce. So I have that filling line as a leading machine, which is then determining the output for the other machines. To also achieve that the filling machine always runs, I need buffers. I have to ensure that the filling machine always has enough bottles to fill, and that there's always enough space to transport the filled bottles. So that we have anti-staff bottles that are buffers before the filling machine, and they are always filled because the machine always needs bottles. Yeah, this is like the anti-staff bottle buffer. And then the anti-block buffer is buffer after the filling machine, and they should be always empty. If these ones are empty or these ones are full, then the filling machine has to stop because it doesn't have bottles or it doesn't can transport the bottles away. So these are the buffers. You see then there's always some buffer space in those filling lines. Here, always filled, and here, always empty, the anti-staff buffers. Okay. Then the first big machine, the bottle cleaning machine. Yes, of course, very important for returnable filling line. Okay, initial situations and aims of cleaning. We can just imagine when the bottle comes into the filling, we have product residues, we have some microorganisms, of course, inside, maybe even sometimes mold if it's standing there. The bottle still has labels, and if they have labels, they still have label glues. They can be foil, for example, inside. There can be dust inside, but there can be everything inside. Like, for example, glass splinters, crown caps, cigarette stumps, and whatever. And this is, of course, something which has to be removed from the bottle. So how can we define the clean bottle? The bottle, the temperature actually doesn't have to do now something a lot with the cleanness, but it's very important then later for the filling process. They should be optical clean, so you should not see any dirt, and also, of course, no objects. Neutral smell, fully wettable, no pathogenic or beer spoiling microorganisms. Of course, they cannot be sterile, but they can be there without risky microorganisms, either for the product or for our health. And of course, they have to be residual free of the chemicals. So the chemical used for cleaning has to be removed from the bottles in some extent. For example, we have here the surfactants, non-ionic surfactants. The surface tension should be above a certain amount, and the chemical oxygen amount should be also below some threshold. So this is something you can then, if you are setting up your machine, and maybe also like for some intervals, you can check if the bottles are really free of chemicals. When talking about the cleaning process, we always talk about, there's always this model of that Sinner circle, which has like the basics of the filling or the parameters of filling, which are temperature, mechanics, time, and chemistry. And usually it says if you reduce one of those parameters, you have to increase another one to have the same cleaning effect. Yeah. When we're now looking at the bottle cleaning machine, according to those Sinners factors, the chemistry, first of all, it is the concentration of the chemistry we are adding. Usually we have sodium hydroxide, so caustic, soda caustic, in a concentrations around 2%. Then the composition of the chemistry, we usually then add some additives like surfactants, later on more about this, and of course it's water. Then temperature, the temperature of the cleaning machine, of the cleaning agent, of course, we are usually around 80%. Mechanical treatment, we are somehow limited in that bottle cleaning machine, but we will see later that we have some pressure, some sprayings and flushings inside the machine, and then the time. The time inside the main caustic is usually around 6 minutes, 6 to 9 minutes, and then we have later some treatments at single stations. When talking about bottle cleaning machines, we can divide, or we can they divide into two main designs. One is a double-end cleaning machine, and the other one is a single-end machine. Here you see some parts of the double-end machine, means the bottles are leaving the machine on one side, then go to the machine and leaving the machine and on the other side. Yeah, and the single-end bottle cleaning machines there's an infeed and the outlet of the bottle is at the same side. There are some advantages and disadvantages. For example, the most advantage of that double-end machine is that you have a more hygienic way. The risk of recontaminations is less because you don't have the dirty and the clean bottles at the same side. In some breweries, it's even made like that. The infeed of the bottles is as a different place of the building than the outlet. Yeah, that there's a wall, and then I can divide the dry part with the wet part of the filling. Very good. However, they have need more space. They are more expensive than the single and double machines. Yes, the entire treatment is also a bit longer. We have here 15 to 25 minutes and a soaking time in the main caustic for 10 minutes. And yes, the single end machines are more compact. So they don't need more space, and short soaking time 6 to 8 minutes, entire treatment 11 to 13 minutes. So also like do that compact design that I can work a bit faster with then. Yeah, but as said, it's like a hygienic risk. So you really have to be see that you don't have such a, it's not so close. And also very important is that always the dirty bottles are down and the clean bottles are leaving the machine from the upside. Otherwise, of course, there could dirt fall into the bottle. So, but if you have a good hygienic concept, of course, you can also work very well with that single end cleaning machines. Inside the machine, the bottles are located in those baskets, usually made of metal, of plastic, but also there exists some made of metal. And those baskets, where one bottle is always inside, they are like on that conveyor things where the baskets are there. Yes, the baskets are important for the uptake and the transport, and also later for the release of the bottles. Also important that the bottles then are centered. You see here the things that the bottle opening, the bottle finish is always here centered in the middle of those conveyors. This is important for flushing and spraying, also then later for the label removement. What other things for the it's important for those conveyors, for those baskets, that I don't want to have a lot of caustic carryover, because this of course will increase the consumption if I carry caustic from one bus to the other bus with those layers. So this should be minimized, and also low heat capacity, also because then of course I would if they take and transport a lot of heat, this would also reduce my efficiency. Okay, let's go now to the different steps of the bottle cleaning machine. We start here with the number 1, with the infeed. And after the infeed, we are having the pre-soaking bath, in this case number 1, and the pre-coat soaking bath number 2. So infeed, of course, is to get the bottles into the machine. The pre-soaking, the first steps of the bottle cleaning machine, there are 2 main effects, 2 main features of what I do with that. First of all, I already have some kind of a cleaning. Yeah, maybe some objects are going out, for example, they are falling inside and so on. But also very important is that I have a heating up of the bottles. Yeah, this first is about 20 to 30 degrees, and the next one is to 40 degrees. So I have a stepwise increase of the temperature, that later when the bottles are going to the 80-degree caustic, don't have such a big temperature shock. You see here that this pre-soaking bath number 1 is filled due to the pre-soaking bath, to the overflow of pre-soaking bath 3. And pre-soaking bath 3 somehow is filled then here to that overflow, which comes later from the water zones. Yeah, we will talk about all that water cascade later, but know for you as an information that those baths are always filled with the water from other baths, and I usually don't have any active heating. It has to be when the bottle is then the machine is working in an equilibrium, that I have a very good exchange of all the baths, so that every bath has a desired temperature. Okay, yes, then this is the overflow from the water, and then here is a pre-soaking bath number 3, which is about 60 degrees, and which is then fed by somehow the main caustic. Yeah, but we have here 20 to 30, 40, 60, and then we go to the main caustic bath with 80 to 85 degrees, and this entire treatment time here, when the bottles are in that caustic, is about 6 to 8 minutes in this example, and we have a temperature of 80 to 85 degrees. As already said, it's NaOH, the main caustic, component, the main chemistry. Additives 0 to 0.1 to 0.3. Very important are that surfactants, which are increasing the cleaning capability. We have anti-foam substances to prevent foaming, and then we have some complexing agents, for example, to prevent destoning effects. Secretions agents also, because I have then always, as we see later, formation of carbonates. And of course, there is dirt in the caustic baths, broken glass, labels, residues from the bottle. And then also, as I said, I have carbonates, but we talk about this later. Now, very important, the label removal. We have usually one label removal inside the caustic and one later outside the caustic, and then here the label discharge. Let's see as a video. This is here, this part and this part. You see now in the video. So here you see a flushing, and also you see the flushing, and they are responsible for the label remove. And we see that now. See the bottles. You see now here the labels are removing then from the bottles. And I have like the pump here, I have a certain circulation of my caustic, so that when that label here is removed, it is then because of that circulation, goes this way like it goes now. Okay, here was one which was not removed, but we see later, but goes this way and then comes here, flows over, and here's a sieve, and then I have my conveyor to take out the labels. So, and you see here's the label still on, which was here, and then I have my second label removed from here, and then again, you got the caustic flows in this way, and the label removes to that sieve, then it's then discharged.
Is there any circulation inside the bottles, or it's just soaking, or
Inside the bottles right now, not. In
no?
this is just talking. This is like we have like with the circulation of the caustic due to that label remove and also for homogenization effects. But inside the bottle, they are just in this moment they are just filled with the hot caustic. But we will have something later. Okay, just as like the heat exchanger, for example, to heat the caustic. So here we put the primary energy. So, but now we have now this caustic jets and caustic circulation and combining. So you see here uh, in this thing we have here like a jet, like a spraying jet, which is then spraying hot caustic inside the bottles. Yeah. Um, so this is the 13 years. And after the caustic, you see here like we have 1, 2, 3, 4 of those bars, which in this time again decreasing temperatures. And with water, and in the beginning this is water, but as I said, if the machine works in equilibrium, we then have in this like still a caustic of 0.2% due to those carryover effects of the bottles and the conveyors, yeah? And after I sprayed here with hot caustic inside the bottles, here then I have like hot water with a bit of caustic and I spray the bottles. And temperature of 60 to 70 degrees. And you see here, these are those jetters, these jets. We have nozzles which are 2 to 4 diameter, pressure 2 to 2.5 bars, and time 3 to 4 seconds. And you see here, the bottles move in this way. And this jetter here is moved by, here's that star wheel. And you see here the bottle or the conveyor is pushing this to the next position. And in this way, I have here first the spraying, which is more to the right side. Then I have here like a centric spraying, and then it moves, and into that way, I have it on the left side. So it moves away with the bottle together with the bottles. The bottle moves that thing, and therefore I have here those effects. And this is to ensure that I reach all inner surfaces of the bottle. Okay, and as I said, afterwards we then have the second, the warm water jet, now with a 55 to 60 degrees, and that number 16 we are at 50 to 55 centigrades, and then with a decreasing pH, so less caustic. Then cold water. It's now with 30 to 35 degrees. And then then I have in the end I have the fresh water. The fresh water is very important because this water is the main thing to get out the chemicals. And then to bring the bottle to a temperature when it reached the filling machine of 20 degrees, because I fill very cold, and if the bottle would be too hot, I would have excessive bottle burst at the filling machine. Yeah. Yes, and this water has to be the quality of drinking water. Quality of drinking water. Sometimes maybe you can even add some disinfectants, such like chloride dioxide and so on, but of course only in the amount that it is within the legal regulations. Okay. Yeah, then In the end, then the bottle discharge, which is like more or less like, yes, of course, done um, with those um, um, machines, which are then putting the bottles from the conveyors into that baskets and vice versa. Okay, but just like that, we see here the way the of the water in the bottle cleaning machine. We put fresh water in the machine. I think more or less a tenth of the bottle's filling volume. So 500 milliliter means 550 milliliters per bottle. And there are those things. So in the end, we put here a lot of fresh water. So this fresh water has to go somewhere, and of course it's inside the bottle, and then it flows to this bars. Yeah. And after a certain time, this bars will then overflow to this bar, and this bar will overflow to here, and then we have that overflow, which is then here feeding the pre-soaking area. And on the other side, I have that effect on the other side with that water here from the hot caustic, which is then also eventually flows. And in the end, I have an equilibrium, and then have that cascade situation and all the bars in the desired temperature. Average consumptions now, yes, for 0.5 milliliter bottles. Okay, here says water still like 120 to 200 milliliters of fresh water. Okay, in the end, not only that fresh water, but the overall water we would need. You see, like, okay, there were like big steps in the okay, 1980 is also now still quite a long time ago. But of course, this is something where you can still try to optimize nowadays the water consumption. Also, this thermal heat, which are now between 25 to 35 millijoule per 1,000 bottles. Actually, that are values from 2008. So they are. I did not find now more actual data, but this is of course also 2008. It is also now 15 years ago, even more. So might of course have changed a lot. In AOH, 500 grams per 1,000 bottles. Yeah. You see here in the end, it says 1.5 to 3.5 euros per 1,000 bottles. But I would not now say that this is like that number we can now trust anymore, because we all know what happened within the last years, that we, of course, had an explosion in all those in thermal heat and also in the caustic, which was increasing a lot. So these numbers we should maybe see that we make new studies to present then more recent, more actual data. But this was like, but I think here's still like between 1.5 euros and 3.5 euros. It's still like a bit gap. So, but I think it's more like now in this range. Okay, that was the bottle cleaning machine. Now we are going to the next machine, the empty bottle inspection machines. Yes, you see here we have the bottle cleaning machine, single end machine in our case. We have that coming out of the bulk. We have here our pressure-free bottle separation, and then they are entering here the empty bottle inspection machine called EBI. To make it a bit shorter, it's an empty bottle inspection machine. It's an EBI. Also, even in Germany or whatever, everybody says EBI or just inspector. Okay, this would be like the more primitive and old form, but it's still sometimes even, of course, how big the brewery is and where it is located. But this is like that inspecting screen, light screen. Actually, this is in this case, it is a light, and you see the bottles, and then manually, first of all, you see with human eyes to see how the bottles, if their bottles are clean, of course, in some extent, and yeah, if there are some objects. However, here are some things which to be considered. Of course, you are quite limited in the output. Yeah, if it's too fast, you don't see anything. Anyway, I think it's not now state of the art. Of course, change interval for personal 20 to 30 minutes. if it's done right. I don't know if this is always when you are like in a market where this is inspector, that this is somebody who this is like taking into account. You just have sidewall inspections. You just can watch from one side only. Also for the bottom mount. You don't see the bottom inspector, and you also don't see residual liquids. Maybe you can see it, but they must be very good, but that must be very big. So this is not actually what it is nowadays. You have that inline fully inspection machines. Here, like a sketch of it, like this is like the linear output in this case, and we have a maximum output in this case of 70 to 75,000 bottles per hour. Yeah, and usually it worked. Here are some pictures of those machines here from Krones and Heuft. These are like, I think, the now world leading manufacturers of that inspection machines. And so they have different functions. First of all, the contour and color detection, yeah. So actually, normally these machines, they have different techniques. Also in one machine, we have different modules which are responsible for different tasks, and they are different techniques. But this is like the EB, that contour and color detection would be that there's a picture made of the bottle, and then it's then compared to a template and see if there's a difference. Or for example, to color, they have put the color scheme that you can see then something like this. If there is a different, then if it's a different, then it's sent to the machine that this bottle is not right. For example, here, this is something when we have here, like this is more or less 0.3 bottles in the German market. All are different, but all are quite similar. And this is, for example, which is then here with the contour, container and color detection, where then the pictures are taken here. Here's those pictures, and then compared to those templates to see if those bottles are right. And also here the same with white bottles, which are quite similar, but not entirely same. Here are some, which is some things where I all looked at the bottles. Surface sealing inspection is of course important, that then I don't have any damages at that surface, at that seal, because then I would have problems while closing, or not while closing, but it is not really closed, so it's not tight enough, container height. Then of course it's only also works with bottles with a thread. Detection of sidewall, contour and container color determination, scuffing. Also, this is somehow like the end of life of a bottle is determined, that it's checked how big the scuffing is, and if that is too big, the bottle is sought out, because now then it's not good anymore. Then we have sidewall inspections, also lower scuffing inspection, residual liquid detection. And then the base inspection, which is also very important, because then we have here something like glass splinters. Glass splinters is actually, I think, the most when filling glass bottles, the biggest hazard. And it is also, so of course you have always in a filling line of glass bottles, you always have glass splinters. There are always effects that the bottle is bursting, and these splinters can always come somehow into the bottles, and therefore it's very important to have a proper glass fragment inspection. However, this is also like the most challenging thing, because the glass splinters of course have the same color and so on, but there's a lot of things happening with that glass splinter inspections, and also with the inspection machines. We make a lot of research with them. I think between 2010 and now, or no, before 2010 or after 2010, there was a big development in those machines, that they were finding almost everything. And now we can say, after like that entrance of artificial intelligence in those machines, we see even now a bigger gap. So these machines can now find some dirt in the size of one time 1 millimeter, and still are able to to separate it from a drop of water, which could be also, of course, on the bottle in that production. So these machines are quite advanced nowadays. Yes, this is like with that CCD cameras with optical filters where those pictures are taking, and then you see here that they are then through the template with that software. So we'll see where might be some things which are not for the bottle. Bottle blower, yes. Before I inspect the bottle, I somehow have to clean the lubricant that I have a proper view on the bottle. Okay. Yes, this were like the empty bottle inspection machines. Now the most important machines, the filling machines. So. Filling machine, then after the inspection machine, working with a closing machine. Okay, we have here classification of filling machines. So here filling machines, and we can make a basic definition and then divide them into weight filling machines and volume filling machines. So we're talking about weight filling machines for beverage. We don't have them, so we can leave them out for now. Volume filling machines. Volume filling machines are metering filling machines, height level filling machines, and time pressure filling machines. Time pressure filling machines we are also not having for beverage production. They are for very, very small amounts, might be for medication and so on. So I will not talk about them. Actually, I don't know anything about them. But then we can talk about the other things. For bottles, very common are height level filling machines. Height level filling machines means that they are that's the filling process. So when the bottle no, when the bottle is filled is stopped when reaching a certain height. Yeah. There are multi-chamber and single-chamber filling machines. I will talk about that difference later, but these are like usually those tools are the most common machines when like height-level filling machines when filling glass bottles. For example, I can also use metering filling machines and flow meter filling machines. Metering machines, I have a metering chamber where I have measure a certain amount, which I then put in the bottle, or flow meter where I have that EDM or mass flow meters, and then measuring the amount. This I usually, for example, use when I fill cans. The reason is the can has a much bigger diameter. And if I then use a height filling level machine and just have a small variance in the height level, meaning due to that big diameter is a big variance in the volume. So this is why I cannot use those machines for cans. But for example, for glass bottles, I can use them. Yes, it's more like the classification. You see here we have maybe a different picture later on, but over the bottle there's always like then the vessel, which is like a carousel, and that's why it's called the ring vessel. And in that ring vessel, the beer is there, and there's also CO2, just like basic. But this is not what it's now about. It's about still the classification of the filling machines, and now it's a filling valve. This one here, the tubeless filling. This is a vent tube, return gas pipes. This is what is usually done for beer. Yeah, when I fill, the bottle here is attached to the filling machine, and I open the valve, and the beer flows here along the sidewall of the bottle. So it is here the sidewall of the bottles, and then the gas which is in the bottle is then pushed back to that pipe inside this. So this is usually what you're doing for beer. But it's not the only way. What you cannot do for beer is that short tube filling, where actually here the liquid would come out of this short tube, and it's usually not done with something with CO2 and especially beer not, which is oxygen sensitive, because you will then, if you just imagine how it would be if you put here like the thing, you will have big turbulences and so on. This is not done for beer. What is done, and actually also quite good, is that long filling tube, where you have that filling to the bottle end, and then you fill it, and then again, the beer fills from down, and then pushes the gas back here. Yeah. For oxygen levels, which is quite important, we will see now, this is preferable. However, if you have different bottle formats, yeah, for example, different size of bottles, and you have to change this one, you would always have to change every of that valve. And here you just have to make fewer attachments, yeah. So this is okay. Objectives of filling. What are the objectives of filling? I think most obvious is getting beer from the tank or whatever into a container. For example, a bottle of a can. This is why we are doing all that stuff. There are challenges. I have beer which is foaming, and I want to do it very quick. Filling process has to be done within a few seconds. This is why I have to fill with a pressure. I have to fill with a filling pressure to prevent foaming and to be able to fill that fast. And the filling pressure has to be slightly above the saturation pressure of the beverage. So 0.5 to 1.5 bar higher than the saturation pressure of the beverage. The saturation pressure of the beverage depends on the CO2 in the product. This is something I don't want to change. It is a product given. I want to have my beer with a certain amount of CO2. But for example, the temperature I can change. This is why we fill with low temperature, because then the saturation pressure is low, and this is why we can have the lower filling pressure. And also one very important objective of filling, of course, is to minimize the influence of on the product quality. Yeah, this is of course what we do, and maybe you know already what is the main influence on the product quality. Of course, it is oxygen. We talk about this then later a bit, but this is something really one of the most important things with filling is with all that. Okay, after getting the beer into the bottle is getting the beer into the bottle with a low oxygen uptake. So here we see like that here's a filling machine. We have here the infeed of the bottle, and then here the filling process in that ring vessel, in that carousel, and afterwards the bottles are out. And there are different things happening. So the empty bottles are going inside the machine. As I said, oxygen is a very big thing while filling, and the bottles, when they enter the machine, they are full of air, meaning full of oxygen. And then I have an evacuation, which I can do with bottles. And evacuation, I put a vacuum on the bottle and taking out the air. In this case, I make it 2 times. And in between, I have a CO2 flushing, also to put the new thing that I can evacuate again. And also with that flushing, I also have like a form of rinsing air out to achieve lower oxygen levels. Yeah. Afterwards, there's a pressurization. I put the bottle into the filling pressure, which is slightly above the saturation pressure, and then I have my filling phase. And after filling, I have the pressure release, and afterwards, then the bottles are going out, and I can crown and have the bottled beer. We already had that pictures with that valve. So we have here that tubeless filler. And here, you see here, it's dark blue, meaning the bottle is full of air. And the first thing is the evacuation. Here, would be the connection to the gas phase of the ring vessel. It's closed. Here I have the evacuation channel. Here would be somehow the evacuation pump, and I'm taking out now, as the first step in that evacuation, that air. I do then a flushing in between and another evacuation, and then I start with the pressurization. Pressurization, I open the way to the gas, to the CO2. And then there's an equilibrium between the CO2 here and the CO2 in the bottle, means that the bottle is on filling pressure, and here it's still closed, but afterwards I can then start the filling. So the beer flows here from the tank through here's some spreaders, and then flows on the sidewall with a low, not turbulent flow, and then the gas is pushed back into here. And this, the height of that return gas pipe where the air is pushed back, is very important, because this is then also here filling end. And this is when some is reached here, which is determined there, is then determined the end of the filling. Yeah, the final filling height is defined by the height of the return gas pipe. I have there some slides. Yes, we can see here. You see here, that is that return gas pipe that we had here, yeah? And here it says, here's a probe, meaning when there is liquid coming to that probe, we get an input. There's a small shortcut, and we know that the beer reached that level of height. And therefore, we can stop the filling process. This is done by the height filling levels. Yes, we have it here. If you see here, this is like that return gas pipe, and here here's that probe. And you see here, we have it here. So we have now the bottle on that filling valve, and then we start filling until we are here. This is like the conductivity, what we have here, and it doesn't change anything. Once this point is reached, here, the beer is here, we have here, like going down of the conductivity, we have a small shortcut, and then we have here now, here now nothing changed, because we have here some insulation material, but in the end, when we then reach this, we know we are now at the very end, and we stop the filling process. And so with that steps, we can then adjust the filling height. So the filling process we know here, and now it's almost the end. Then usually the filling speed is slowed down a bit, and then afterwards we have those things, and then with that we can then handle and steer the filled height. This is the height filling machine, yeah. Here, this is from our pilot plant, our old filling machine, one step, and it's quite good to see those different steps here of pre-evacuation, CO2 flushing, and then filling. Okay, we have here now some overflow, but you see here all those first, then evacuation, and then flushing, evacuation, flushing, and then pressurization, and then the beer is filled without foaming, only after pressure release. I don't know, it's not so well adjusted in this case because we have that over foaming, but however, this is also then, if we close them fast enough, it's very good for the oxygen levels. Yeah, and here already says TPO influencing factor. TPO means total package oxygen, and this is the most important factor concerning oxygen in this case. So oxygen, and especially like the TPO, the influence of oxygen in bottled beer. Oxygen, of course, reduces the shelf life, leads to off flavors and color change, and so on and so on. I think some other teacher already told you that. And the TPO, that total package oxygen, is actually the sum of the oxygen load at the beer at the filler inlet. So maybe the oxygen, what comes into with infiltration and so on. And then the oxygen uptake during filling and the remaining oxygen in the headspace of the bottle. And here are some values in the 1987s. This is, of course, for big breweries, yeah? If you are having small breweries, maybe you will not achieve these values. Then you have to, for example, work with a reduced shelf life, no problem, just drink the beer fast. Then you don't have that oxidation aging processes, whatever. Like we said, like in the 1987 was that MEBAC, that SOP methods for brewers, and they said like it should be like 1 milligram or below 1 milligram per liter. So it's 1 ppm, 1000 ppb. Usually nowadays they talk about ppb in this case. Modern filling lines with optimized processes nowadays should be below 100 ppb, 0.1 milligram per liter. Yeah, actually it can be even better, but this is some like a value below 100 is something you should aim for. Okay, what is influencing the TPO? What is influencing the TPO? The oxygen load of the beer at the filler inlet. So I'm talking about filling and packaging. So this is not my thing. This is I cannot influence in this case. This has to be done by the filtration guys or whoever was handling the beer before. But this is also influencing the TPO, but not handled by with me. But then oxygen uptake during filling to contact between beer with air. So pre-evacuation to remove air from the bottles before filling. We had that. So we take out the air. CO2 flushing. Low filling pressure, it's important because of two things, because of the laminar beer flow during bottle filling, and also has to do something with the CO2 purity. I'm going to talk that later. And of course, reduce beer to air surface. Yes, high CO2 purity. Usually it's not always 100% CO2. It's 99.9 or whatever. And there are always some contaminations with oxygen in the CO2. And very important, the remaining oxygen in the headspace of the bottle. And then we have here one of the most important gadgets we have at filling is a HPI, the high pressure injection. Yeah. Okay. So low filling pressure. Filling pressure as low as possible. Yes, because the amount of air inside the pressurized bottle, CO2 consumption, and the time for pressure release phase. Minimum filling pressure, we were talking about it. So this we have here this, yes, actually the low filling pressure. Here is some example. Actually, I don't think it's necessary that we now go to every step. Maybe you have all the presentation. You can then look at it in detail for yourself. But what is very important, or what is the main statement of this? That I have impurities, so there is not 100% CO2. I have, in this case, just an example, 99% CO2 and 1%, yes, 99.0. So yes, 1% of oxygen. So, and now here is a filling pressure, 3 bar, meaning the higher the filling pressure is, the more of that CO2 I have to put inside the bottle, and the more oxygen I have due to impurities. Yeah. And this is why I should have the filling pressure as low as possible regarding the oxygen, because the lower the filling pressure, the lower of that CO2 I have to put, and the lower the contaminations due to impurities. And of course, this is something I said, that the beer is pushed back, the CO2 is pushed back into the channel. And then over the time, I'm putting more and more oxygen. And this is why also the filling pressure should be low as possible. Yes, and this is of course with can be influenced with the temperature. Here is like the amount of CO2, and then, for example, if we have here 7 grams per kilogram per liter in wheat beer, at 2 degrees we have a pressure of 2.5. Saturation pressure is 2.55, and at 8 degrees would be 3.5, 3.5. So this is why we can then reduce the filling pressure when we are filling the beverage cold.
Can I just ask? Can I ask about the CO2? If it's 99% CO2, is it always 1% oxygen, or are there other gases there as nitrogen, or should it?
I think usually it's oxygen or it's air. I would say this is the
so it's
impurity.
air. So.
And that please, that 99 is just an example to have that calculations. Yeah, there's always specification. There's this, you can buy CO2 with different purities, and of course, the higher the purity is, the more expensive it is. But yeah. Okay, yes, just another thing which is also not even regarding the TPO, but the for the low filling pressure, of course, the lower the filling pressure is, the less the bottle burst you have here. Here's just some example for a beer bottle, where you have nowadays 0.005 to 0.0004% means more or less every 20,000 bottle is exploding at the filling machine. If you have a big filling machine, maybe 60,000 or up to, the mean, like, would be meaning 3 bottles per hour. And so you can imagine that that is making a lot of glass splinters, which can then um, contaminate the bottles. Okay, this now is another example where it says, like, the high, which is important for the high CO2 purity. Yeah. So we have the return gas, which is here, contains in this example 1.3% air in that two-step evacuation. And this is how we are then contaminating the CO2 atmosphere and the ring vessel during filling in that so-called one chamber. In the beginning of the classification, we already talked about the one and the two chamber fillers, and that is in the one chamber filler. And now this now is a two channel filler. The big difference is, you see here, like, it is a bit now a different design, but it's more or less the same. But we have here the beverage and the CO2. But the return gas, it's not going back into that chamber. It goes in a return gas channel in a separate chamber. Yeah. And then I could take the CO2, and maybe I can make then some CO2 treatment to get it again pure, to have it then for further production processes. But in this case, in that multi-chamber filling machines, then you have much lower much lower oxygen contamination during filling, obviously. Yeah. What, of course, it means higher CO2 consumption. Yeah. You have a higher CO2 consumption in this case. Of course, you can then regenerate the CO2, but yeah, this is like, I don't know, some companies, the very big ones, want to have very low TPO, and then they use those machines. Here you see return gas pipes, and here are those spreaders. Of course, you should see that they are intact, because then, of course, they are like leading to a turbulent flow. That we already had. Okay. I think maybe now would be a good time for a small break. We are 90 minutes more or less. Are you okay?
Yeah, it's great.
Yeah. So would it be okay for you if we meet at 11 again?
Yes. That's great.
11?
11.
Okay, good.
Yes. See you then. There.
Okay. Yes, we are not yet over with the TPO, and just regarding the remaining air in the headspace after filling. As I said, like, just in the beginning, that a half a liter beer bottle usually had a rimful amount of 520 milliliters, meaning that I have their air. So oxygen content in air at 20 degrees. Here's some big requirements. It says like 1 milliliter of air contains 0.1 milliliter of oxygen. It's 0.28 milligram of oxygen and 1 milliliter of air. So if I now have that 20 milliliters more inside that that bottle, I can now see 20 20 times that 0.28 is then we have 5.6 milligram of oxygen in the headspace. Because we're talking about a half a liter bottle, means that 20 milliliters of air means 11.2 milligrams of oxygen in the bottle. And when we said like we were like with around 0.1 milligrams per liter, what is nowadays to achieve, we are then a factor 100 more than required, meaning the remaining air in the headspace of the bottle has to be removed. And this are we doing with the high pressure injection. This is very, as I said, one of the most important gadgets. And we see it here. This is a high pressure injection. And actually we are then jetting there inside the bottle sterile and oxygen-free water. Sterile and oxygen-free by means of just heating it, yeah? So we put the hot water, I don't know, 80 degrees and so on, put in the bottle, and due to that, getting the water inside there, we create an overfoaming of the bottle, and therefore the oxygen is pushed out, and then we have to cap, of course, in the right moment. You see here a small, like a head, like a capuche of Schaum, where we then have it here, and then we put there the crown, and therefore we achieve we can put out the air in the headspace. Yeah. Here you see also some other videos. Here's the crowning machine, and then here's the API. We have then directly before filling, we then have the moment where we pushed it out. You see here, this is the right amount of foam at the closing machine. Here is the jet of the high pressure injection. Okay. Modern glass bottles, so different values. We already had that. Here says below 150 ppb. We say below 100. Uptake during filling is 0.02 milligram. And then the CO2 consumption, 220 to 200 grams CO2 per 100 liter of beer. And then we have a beer loss of HBI is 0.5 to 1.5 milliliters per bottle, what we are losing due to that overfoaming. However, we should happily take that loss, because then that means that we have good oxygen values. And then, of course, a filling height deviation of plus minus 1.5 milliliters. Okay, what we said realistic, this is what we say, under 100 ppb, but we already saw, for example, an acceptance test that we can have values below 40 ppb. Very important, of course, to control the TPO is that you measure it right, yeah? And I think that is somebody, even the smallest brewery, should be able to measure the TPO in their products. There are machines especially for that. For example, from Anton Paz, the TPO 5000, which costs, I don't know, more than 50,000 euros. Of course, this is not it's not acceptable for everybody. However, I think most of the breweries have something like this, or some other measurements to measure the oxygen. Maybe not the TPO, but the dissolved oxygen. In this case, that Huffmannsgehaltemeter, but also like there is that DGOX, I think, or Carbodiox from Anton Paz. So there are also some other methods to check the oxygen. However, to check the TPO, you would need something more. For example, actually, it's just a shaking machine and something like a tapping apparatus, how to be able to take the beer from the bottle inside that thing. Because we can then apply the MEBAC method, B 420, 29, 9000 now. That is all, and to measure the total oxygen in beer and cans. So where is the oxygen right? So with that machine, I cannot measure the TPO. I measure the dissolved oxygen in the beverage. This is important. Okay, where is the oxygen right after filling? This, first of all, is the beer, and we have oxygen dissolved in the beer. Should be not so much, which is basically the oxygen load at the beer at the filler inlet, so what comes in, and the oxygen picked up during filling, which should not be so much. Most of the oxygen should be in the headspace. that was not removed properly by the HPI. Yeah. What we are now doing, we are shaking the bottles and then achieving an equilibrium between those things. So the oxygen in the headspace and the dissolved oxygen are getting into equilibrium. You see here, we shake before for 5 minutes. And to now calculate the TPO, what do we need? We need now the oxygen dissolved in the beverage that we can measure with a Huffman's, with the machine if we have that piercing device. What we also need is the temperature of the beverage. It's given in the measurement devices usually, the filling volume, and the headspace volume. And these are some things we can find out by metering, for example, by just weighing the bottle and then calculate by the density. Yeah. And then we need the ratio between the filling volume and the headspace. And then with this information, we can calculate the factor Z. And the factor Z we multiply with the oxygen we have we measured, and this is how we can get the TPO. Okay, so we have to shake the bottle, measure the oxygen, and then make those calculations. Here are some stepwise SOPs, some stepwise instructions how to make it for example, we have it here for glass bottles, for cans, and also for swing top bottles. I think we don't have to now go through everything in detail, but this is for you. You have all that things. If you want to know, this is how to make it then properly. Yeah. For example, with the glass bottles, mass, we have to calculate MA, which is the mass of the bottle plus the crown cap plus the beverage, and then measure within 20 minutes. Mebach says within 2 hours. We say 20 minutes, 5 minutes shaking, 5 minutes resting, and then measuring the oxygen. Measure the temperature. The temperature of the beverage is shown on the measurement device, calculated then to Kelvin. Then we have the mass of the empty bottle, and then we have the mass of the whole bottle. We fill it full with water. Then we have make a calculation for the density. In the end, you can then have that factor Z, and then you can make the TPO. As this is now very, very rough and very, very, very unprecise. However, but what I'm now going to tell you is very unprecise. But if you want to make it quick and dirty, you can just assume that the Z factor is around 2. Yeah. With bottles, maybe 2.5, but for example, with cans, it's around 2. Yeah. If you want to just have an indication, if you are good and so on, you can just shake, measure, and then with cans or bottles, makes between 2.5 and 2, and then you have that. Yeah, especially when you have, for example, for cans and so on, when you have like a pretty high, pretty precise constant fill level and also high constant temperature, you can then make that Z times maybe 10 times, then make an average, and then you have a good way. Yeah. But this is how it's made, and then of course when you have the TPO, you can know now how to maybe improve your process. We have here, I think, the last year that we did it, and then we made some research, some investigations, and then had here like some values we found out with excellent real life TPO values with an HPI, and here are some bottle types. And then we were here between 50 and 20 ppb, as very good, very much below that 100 we are saying. And then for some other things, we checked the values without using the HPI. And you see here, we were like factor 1000, yeah, without that HPI. Yeah, so seeing it is 1000, no, 200, doesn't matter. Much higher without the HPI. So that is very crucial to have the HPI when filling bottles. So Okay, now we are talking about we had the glass bottle filling machines, and now we are leaving that machine and put the next machine right next to it is a closing machine. So usually blocked. We saw that already, that they have to be like quite close to the filling machine, because we want to use that over foaming and have to close them. Just some words now to the crown corks. Usually nowadays we have here some coating, for example, chromium oxide style. Thickness, we are going now to somehow reduce the weight. So nowadays we can see there is that standard of 0.235 millimeters of thickness. We have a lacquering, we have a printing, and we have that compound. Usually in that compound, often we have some oxygen scavenger materials, some things which are reacting with the oxygen before the beer reacts with the oxygen, and therefore we have then lower effect of oxygen coming through the crown corks inside the bottle. Here, this is maybe you remember the very beginning of this morning when we are talking about the hot end coating, which was a metal, and of course we are even said it was titanium or so on. So we have a different Nobel distance of those two metals, and then together with liquid and so on, we can have that corrosion. This is why that hot end coating should not be in this part, yeah? So usually you define the hot end coating should be here, but should not be at the finish, because then you would have that rusty effect with the crown corks. Here some methods how it is like the crown corks are fed into the machine. Usually you have that big cardboard boxes with, I don't know, 100,000 or more of those crown corks, and somehow they have to come to the clothing machine. And of course, it's very important that those crowns are coming to the clothing machines in the right direction. And this is often you see nowadays those kind of alignment machines like this. It's just like here is the storage of the crowns, and then I don't know, by random they are coming into those guidings, and then they are going up, and due to the gravity forces, only the ones which are in the right directions are transporting up. You see here. So in the end, you have enough crown corks to feed them in all the right directions. The ones which are the wrong direction are just falling down. So this is how it's used to be, but there are different different ways. So this is like then the turning here, in this case, the turning tube. We have a different sketch of that, but then here is like the crown cork slide. And then here, like then how the crowns are then coming to the crowning machine. This is a turning tube also to ensure that the crown is in the right direction. So anyway, it is like just mechanically, you see here those slots, and then the crown fells, and then however it comes here, it has to be turned, and in the end, doesn't matter if it's this or this side, how it comes, it makes a turn, and then will be always in here at the right direction. You see, I don't know, it's not easy to see in those videos, but I think you can imagine, no, that we have some ways, so like it's a mechanical done that the crowns are all in this right direction. Now to the closing process. Actually, it is quite simple. We have those crown. Here you see the bottle, and here's that compound, that titanium material, and here the crown itself. And this is the bottle. And then we have here like the compression die, where we push first the crown that it holds on the bottle, and then afterward there's a closing ring which has to be in a defined diameter, which is then just like a stamp, hits on that on the crown here, and then presses the metal and the compound to the bottle that is tightened. Yeah. It's not now rocket science. Actually, it's like a machine, like, yes, you can imagine it. I don't know, I don't know if you know that hand corkers or that ones where, and it's basically the same, yeah. Okay, here you see, it's easy to imagine, I think, how that preload of the crown clocking, and then we have that closing ring and defined diameter also according to the bottle and the crown itself, but usually it's standardized that you have then all the same diameters. And of course, you have that you need to have a special force somehow between 1.8 to 2.25 K Newton, that it is tight enough but not too tight, because of course if something is too tight, then it is destroying. Yes, then next thing is the bottle shower and drying stations. You remember those videos with the HPI, the foaming of the bottles? Of course, the bottles then are full on the outside, full of beer. This has to be removed because, of course, it has to be removed. Yes, because. And then afterwards it is removed, and then usually you have then a bottle dryer also, that the bottles are afterwards then dried, I don't know, to be maybe in this case able to labeled if there's no pasteurizer in between here, but also like a very simple machine, that bottle shower. You see here that after the filling machine, there's water. Maybe you then also could put there some, I don't know, ClO2 or so to avoid contamination, because you can imagine that is all like a very moisture area, especially then in the filling. You have that over foaming, you have pressure residues, and then that water and so on, and you don't want to have this area. We should be then very promote the growth of microorganisms. And then afterwards here, like a bottle drying with air nozzles. So you just imagine like the thing to dry your hair, the blow dryer of your hair, and something like this, then to afterwards dry the bottles. Okay, that for bottles. Now coming into cans. Actually, we have a lot of similarities, but also some differences when comparing the bottling of cans, or the canning and the bottling. Yeah, usually the can lines are more simple, not more simple, but more compact. Yeah, there are. Just imagine you don't need that big bottle cleaning machine. You don't have anything like that, like that transport of the empty, a lot of transport of empty bottles in crates. So usually this is why they could be often more compact and less machines. However, they can have much higher output. I think the higher the filling machines for bottles, usually you don't want to go above 60,000, yeah, because otherwise then it's getting yeah, I don't know, you have too many interference. However, with cans you can fill up to 120 cans per hour, so can be very big. You see here we have the depelletizer, then we have transfer, mass transfer, vacuum transfer. We will see that later. Also go then to single file. Then we have a filler, a seamer in this case, together like with the sinks, a fill level check, twisting always. And then there's a pasteurizer. Usually that is, or it's often more often used than with beer, the pasteurizer, and then some other things for like a file check, air blower, and then secondary packing machine, for example, the trays. And when we have the trays, maybe we have something, the shrink foil to put and to hold the trays together. Yeah, and then afterwards the pelletizer. What is usually very symbolic, or very often, is that we have two levels in the two height levels in the can filling line. Yeah, this case we will see later. Yes, until here is on a higher level than the filler. Has different reasons. Starting with a depelletizer, you see now here the pellet of the can is very high packed. Yeah, so that usually when I depelletize them, I think we have a video of it. Now you have that thing, we have the depelletizing, but the depelletizing starts already on a higher level. See, when this is the ground floor, then we have that high pellet, and then we have the depelletizing, which is actually, of course, has to be somehow gentle. Here's the different layers of cans. In between, we have some intermediate layers, but we are pushing then the cans to the conveyors of the filling line. And then you see it's actually here, this is then pushed on that. And then we have here the mass conveyor and also pressure-free can separation, similar like done for the bottles. Of course, this is all a bit, we don't have to, they are not as heavy, we don't need so much forces, but we also should, of course, avoid by any means that we have here massive denting of the cans, because this could lead then later to corrosion because of material cracks and so on. Yeah. Okay, but you see the pellets of cans all quite high, and then they are here on that high level coming from the depelletizer and then going from bulk transport into single transport with that separation. Then we had that also in that sketch, we have a vacuum transfer. Yeah, so here the cans are not transferred with a conveyor, they are transferred by vacuum on the upside. You see, they are like somehow not flying, but you know there's a vacuum, and they are transported until they are getting here down again. For a small moment, they are transporting like this. And you see here, I don't know if you see down. Here they are lifting up, yes, and then here's a vacuum transport, and down after the vacuum transport, you see here those that bin. Yeah, it's just like if I have a fallen can on the line, it would not be lifted up, so it will fall down. This machine is then therefore to remove the cans which were falling. Okay, that I don't have interference with some cans which are falling down. This is just made by this vacuum transport, which is usually then in each canning line. Then can inspection machine. Okay, of course we don't expect, it's not like with an empty bottle inspection machine, not like a removable bottle where we have like that very dirty bottles where we can expect everything. We have that can coming from the manufacturer. So there is a lot of in there. They have already some inspection machines. However, there are also some inspection machines for cans. For example, here are some floors which a can could have, which could be then checked more or less precisely, intensively with that inspection of cans. So of course you with it, because it is okay, from the upside you can look in, but on the other side you cannot see so much. You have to then have other technologies than optical, for example, X-ray, to check that. So then the rinser. As I already said, the cans come from the supplier more or less clean. It's not like a dirty bottle coming from the customer. Yeah. However, we should anyway, due to production, storage, transport, depelletizing, and transport and filling line, we could have some contaminations. Yeah. So we don't talk about non-adherent dirt. We talked, for example, about dust, or in this case here, some insects. And this should be removed from the can. And of course, we cannot make it. We don't do that like a bottle cleaning machine. Therefore, we have a rinsing machine. Aims of rinsing cans is to remove those not adherent dirt. That adherent dirt and non-removable, that must be detected in the manufacturing of the supplier of the cans. This is not in the responsibility of the brewery. So, but we call those gravity rinsers, and you see now we have here one level, and here then we go into the ground level, and this is why that is like the rinsing where we are cleaning the cans. You see here, these are those twisters. imagine the can goes to that things, and it's like, I don't know, like a roller coaster or whatever, or like that things for astronauts, where then the can is then rotated in the beginning to 135 degrees, and then has a drop angle of this one of 35 degrees. So we have some cleaning effect due to gravity. Some things, the dirt would be already falling down. However, this thing is also called rinser because we are rinsing. So we put there water. I don't know, for example, water rinse sections. For 2 seconds, we are rinsing the cans with water. Water should be, of course, for some quality. We should avoid, as usually you should use degassed water, but you can also add there some disinfectants like chloride dioxide. However, normally you pasteurize the can afterwards, so micro is not a big issue in this case. But this is then done, and then we have the rinse discharge. We had then first 135 degrees, and then plus 225 is 360. We have then the full inversion. The bottle is turned, and then is then in the right direction, and then can enter the filling machine. Can filling machines. So again, to the classification of the filling machines, I think I already were telling you what is with the cans. We cannot use those height level filling machines with the bottles because the big diameter. I already said that. This is why we have either a metering filling machine or a flow meter filling machine with the cans. There are other things.
Nan, you can ask it, please.
I have a building going on, so I'm not so sure. So, but if you rinse the cans and if there's any water left in them before you fill them, won't that water be fully saturated with oxygen and cause oxygen pickup?
Actually, first of all, of course, you would want to have as least water residues as possible. And second of all, you can, for example, use degassed waters. This is, for example, how we are doing. For rinsing, you need deaerated water.
But deaerated water, as soon as deaerated water meets air, it will be fully saturated with oxygen, right?
Yeah. I don't know how fast that is going to be happen. Usually, you have the filling process directly afterwards. And I don't know, once I made some things. Actually, it was a bottle where I put some water into the bottle, like 1 milliliter, 2 milliliters, and then checked the influence on the TPO, and it was very low, I have to say.
Interesting.
Yeah. It's a very good question. We already also like a lot of we already asked this question. What is the impact? In this case, it was not a big study. So, but we made some trials, and there was not that thing. So I think first of all, you can use deaerated water. Second of all, I think in the end, this doesn't make that big influence. And third of all, you should anyway keep that amount of residual water as low as possible. Yeah. But good question. Okay, we see here then the process now of the can filling. And I think the first thing which might be obvious, there is compared to bottle filling, one important step, or which was important for bottle filling, it's not here, and it's obviously the evacuation. Of course, can just think if you put a vacuum on the can, it will collapse and so on. So this is what you cannot do. So you only have that CO2 rinsing. Of course, you have to make it more excessive than with bottles. I can already tell you that you have much higher CO2 consumptions when filling cans compared to bottles. However, the other steps, so we have the CO2 rinsing, then the pressure rising to the filling pressure, the filling, the calming, and the pressure release. It's similar then like for the bottles. You have then here like a quite long way between the filler and the seamer and the closing machine, but this later on. Yeah. Now, the CO2 rinsing and flushing. Here, actually, this is like the metering thing. Here we have that where the volume is metered, which is then determined by those swimmer. But first, let's talk about the CO2 flushing. Yeah, we have here these channels. I think one is here the CO2 supply, one is the CO2, then the outlet. But in the beginning, we are flushing now, and we see that the centric bell, it's not let down completely, yeah? That is flushing here also to the ambient, because this is that excessive flushing, what I was telling, to be able to remove most of the air, yeah? Only then, in a second step, we then have a rinsing, where we are rinsing then from the here to the return pipe, or the, like, I don't know, I think it must be a multi-chamber to go back to the CO2 thing. Yeah, but first we have that rinsing to the ambient. So then pressurization. So we close that way that the oxygen, that the CO2 can go out. We have the pressurization, and then we have the filling. Here the CO2 goes back, and then you see here that swimmer then in that metering chamber goes down until here the filling length is a certain level is reached, and then afterwards we have both. We have like here a pressure relief, and during the pressure relief, that chamber is filled again with beer to prepare the next step of can filling. Yeah, for the next can, and we have that pressure reliefs. So this is basically like the main difference between bottles, or that height level that I have here with that metering chamber. And as I said already, there is also the way to make it with an with a IDM, with a, for example, in this case here, the flow meter can be a mass flow meter, which is, I think, more precise and but usually you have that IDMs to measure the flow by electric conductivity, and then you know exactly which comes down and which flows down out, and then you could stop the filling process when it's about time. The other thing is the same, flushing to the ambient, flushing back, then pressurization, filling, and pressure relief. Okay, O2 uptake, yeah? Talking about that, we have O2 uptake again, like due to the filling process, like when we penetrate to the seamer, of course, we have initial oxygen load, and we have removing air in the headspace. CO2 rinsing before filling here. Enough pressure to reach the can bottom. Yes, so we have to have a certain pressure. However, excessive pressure leads to CO2 loss with mixing of air. We then can put air inside the bottle. So we have to make that quite precise. And of course, as long as possible, as necessary, it would be better to increase to decrease the movement of on air. One, also, we cannot evacuate, and another disadvantage is that we cannot use an HPI, because also because of that big thing with overfoaming, we would have an excessive loss of beer and lead to underfilled cans. So we need other things to take care about this. And therefore we have a bubble breaker and sublet gas stations. You see here, here I said it could be quite long. We have here like the cans, open cans between the filling machine and then the closer, the seamer. And if you see here now, the foam comes out. This foam is, I think, very coarse, and it's really acting almost like a sponge for taking air from the ambient. Yeah, you see that better. But that means also, if you would remove here the first layer of that foam just before closing, then you would remove most of the air from the headspace, because the air is in that first layer, in that foam, the bubbles. You can, that most of the headspace air is inside there. So And then you use again CO2, destroying large bubble by CO2 flow, remove top layer of foam. This is a bubble breaker. Influence, in fact,
how does the CO2 flow come out of the bubble break? Is it going down or is it going on the side? How does that work? I've never seen this.
Never seen this? Okay, you see here, I don't know that you can of course somehow have to the flow, have to control the flow of the CO2, but it's made in the way that it works. I don't know if it's now comes, maybe there are different systems, if it comes directly to horizontal or if it comes maybe a bit slow. It has to work. I don't know how exactly now the flow is, but it has to be blown away that it's done like this. I think here's another example of this. You see, but I think it's coming horizontally, and then together with the movement of the cans, it works to that have that effect. Yeah. But I think you see here. So actually, it's a spraying it's a spraying of. Oh, now it doesn't work. It's a spraying of that CO2, which is then here very. I think this is very good example how it's then done that the top layer is done. Yeah. And the bubble breaker, and then we have another thing, which is in the seamer. First of all, here, like, we don't have like the crown supply. We have them here, all they come, that can lids come all in the back in a roll, in a big roll, which have already the right direction. So there's no correction necessary in this case. So we have now here the infeed of the thing. So, and you see now we have those different stations here. Of where the cans, the open cans, here are the lids, which are the lids are then here delivered to this, and in this case we have here the bubbles, and here where not the bubbles, the cans, open cans, and here where the lid is put on, we also have here we have that rotating star wheel, we have that static CO2 channel here, and then CO2 channel inside the rotating star wheel. So in the end, it is that this sublit gassing, it's called, it's meaning like in the moment we are putting the lid on the can, we are blowing CO2 under or between lid and thing. Yeah, I think it's a bit hard to see. There's also video, but I think it's I don't know how it's very hard to find this, because of course you cannot see CO2. In this case, you don't have bubbles anymore, but here you see that rotating process while seaming, and in the here somehow where you see here must be that sublit gassing that we are blowing there CO2. Actually, it doesn't have to be CO2 in this case. For example, in our can filler, we built, I think, using nitrogen. Yeah, it has the same effect, and usually nitrogen is a bit cheaper and was now, and you can have nitrogen generator using the ambient air. So this can be also done by nitrogen. Okay, now the TPO of cans. Critical value, I don't know, it says here 1000 ppb, 1 milligram per liter. According to our thing, according to our experience, this cannot be an acceptable limit. I think we are here with 0.25 milligrams per liter, so 250 ppb. This is something maybe should be some which is should be your threshold, your benchmark. Yeah, I think if you want to go way deep lower than that 0.25 milligrams, so 250 ppb, it leads to excessive CO2 consumption. There's this one point where you then just need more CO2, more CO2. This is more or less the only thing you can very optimize, and this is then not anymore than makes sense. You see here, modern can filling line CO2 consumptions, 400 to 500 grams CO2 per hectoliter per 100 liter of beer, and with you're more or less having the half of the CO2 consumptions with the glass filling machines while reaching lower TPL values. And in the end, CO2, just the filling machine, yeah? When you then have the seamer and the seamer with subligations, we are already here with 600 to 800 grams per hectoliter of beer. So much higher CO2 consumption when filling cans. Of course, in cases, I don't know how it was for you, but we had some kind of like a CO2 crisis. Now it's a bit better, but in this case, it's like, yes, it's a thing. However, we all like beer in cans. We all like beer in bottles.
So
you have a question?
Yes, please. So you said that you can use nitrogen gas and you have an own generator for nitrogen gas, and you can use that under the lid, but you can't use it for any of the other steps in filling. Is that right?
You can use it for some. It is something, but you have to see always when there is contact with beer. For example, in the ring vessel, and then you would have nitrogen there, and you would have CO2, then you would have an exchange, and in the end you would lose CO2, yeah? But there are a lot of now research how to use nitrogen instead of CO2. There was new research and so on, and there is a lot of things going on in somehow to reduce the nitrogen and to use more and more nitrogen than CO2. Yeah. You cannot use it for all, like always when there could be like those mixing effects. Sometimes you have then use a mix of nitrogen and CO2 and so on. But for a lot of things you can use. Also for tapping, if you tap fast, yes, if you know that I tapped my keg within the day, no problem. But if I have it then over several days, then I will have an exchange and so we have CO2. Okay. Yeah. Also, even when filling I don't know if it's for you interesting, but for example, when filling water or like bubble-free water and so on, you can also use air, sterile air, and so. But it's I don't know. But you wanted to make beer, and then please don't use air for anything. Okay. So the seamer. Actually, we have two operations, and therefore we have two seaming rolls. This is here like the seaming head. There is the can then coming, and this is like that rolls, which are then making the seam, which are clothing the can, the end to the can. Yes, in first operation, it's two operations. The first operation, the seaming roll forms the curl of the lid of the end under the flank, as illustrated in those cross sections. So you have here the can. This is the lid. And then we have here the can, and then we have the roll, which is then here due to that rolling process forming here that roll, that seam, and for example mixing the layers of forming that layers of the can and the at the end, yeah. And 90% of this seam is formed in this first operation. And here, this is the second operation. The seam is completed by the second operation, seaming roll, and this irons out the 5 thickness of metal. So the 5 layers, 1, 2, 3, 4, 5, formed by the first operations, and performs then the hermetic seal here also with a seaming material. This seaming quality is something you should I don't know how the can line, but I don't know if this is here something important or something relevant for you with 90,000 cans per hour. But for example, if you have that, you should make it every 4 hours. Or below that, more than that, you have to make every 4 hours. Just to say, it is a requirement to seam evaluation frequently. Yes, this is of course a very crucial factor that you have that, and then you have to make proper that seam analysis. Actually, you make here those pictures. And then we have here 1, 2, 3, 4, 1, 2, 3, 4, 5. And you should here check overlapping area to know if that ceiling is good. Yeah. And if that overlapping area is within certain specifications, you know that you have a right good seaming. You won't have any problems with untightness or something like this. And of course, there are software that just say yes or no and calculates all the seams. Okay, now a small jump to filling for pub and craft brewers. Actually, to be honest, it's a pity that we don't have so much experience with that machines. There, of course, what we can say here some typical bottles for I think pub breweries, those swing top bottles, those growlers, something like this. Bottles you can open and close without a special machine, and of course they can be filled more or less professional in a pub or a craft brewery. This is actually a returnable bottle, and then of course we have systems to ever requirement to ever need how to clean those bottles. Here, for example, actually it's I would say it's a mix between a normal dishwasher at home and the industrial bottle cleaning machine. We have, of course, it's specialized for those bottles here, where we can put up to 400 bottles. And here we have special, like, I don't know, the steps are more or less comparable to the ones of the real, or not the real, the big machines. Removal of residues, pre-cleaning with warm water, and then we clean also with 2% of caustic, have a label removal, and 55 to 75 degrees, and then rinsing with fresh water and decreasing temperature steps. Yeah. I think there are, of course, different ways to clean your bottles. Here, other batch processes. Here we have a growler cleaning machine. This just made a picture, so never in real action. This was at the fair in Nuremberg, where that machines were then saying, I don't know, yes, it looks a bit like a laboratory dishwasher, but where you can put the bottles and then you have a program. In the end, it's important that the bottle is clean, and then, of course, there are different ways here. For example, nowadays also, of course, the craft brewers are a big market also for the bigger companies. So also the big suppliers like KHS or Krones have equipment for cleaning bottles. But this is here continuous process. This is actually the machines we had. We were talking in the beginning, but in small, yeah. Output 1,500 to 8,000 bottles per hour is quite a lot of thing, but it's the same. We don't have to hear the steps. You see that actually these machines are often used in companies who are making the mineral water, and then there are second machine for acid, because we have then those of course the minerals will form something which is not removable with caustic. So if then the empty bottle machine inspects something like this, they are sent to that machine which works with acid instead of caustic. But just a side fact. Shelf life. These are some, I don't know. I would not say this is like a number you should always state, and this it is. This is, you have to have your own definition. However, the shelf life, usually higher oxygen uptake during filling to compare to industrial processes. It's always like this. Of course, the bigger the process, the better you can optimize. So we can talk about the shelf life, depending, of course, on the product, on the initial contamination. Cold storage, of course, is preferable. I don't know when you are. I don't like that here is that 6 weeks or 8 to 9 weeks. Just see, but I think usually it's not realistic that craft brewer, pub brewer gives a shelf life like industrial brewery between 6 and 12 months. Yeah, you have to control that. This is also, of course, how professional you could work. CO2 losses during filling, yes, counter pressure filling systems, like in industrial that I have that filling pressure systems, trained employees when using a standard tap, of course, if I don't have that counter pressure systems. But for example, here are some manometers. Of course, this would be like a growler filling machine, but here for sure you have some counter pressure. So it is like you have here, can adjust it to the height. It's of course a quite manual process, but have then the bottle, the growler, put it into the device. Here you see it's somehow tightened and then have that filling valve. And then you would also bring it to a certain pressure and then have it like this. Here, this seems to be more or less the same. Yes, there are, of course, different systems you can use. Actually, this looks a bit adventurous at the first, but somehow it was actually, I think, would work for him perfectly for its purpose. Filling system for siphons, growlers, glass bottles, even those 5-liter things. And it is like you have here that devices where you can then put the bottle and put it to a certain height and can connect it here with those things to tighten it. You have here like something like a ring vessel where you have the beer, where you have the CO2, you have pressure, you can pressurize. Of course, I don't know if you would, maybe you can even, there were valves that you can even make some, okay, vacuum, not, you would need a vacuum pump, but maybe some rinsing. So actually works quite well, and I think there are several manufacturers which have the systems how to fill the bottle. This is something I don't know, the East European, they like to just where we have their plastic bottles, and after the night in the bar they like to take something home. Yes, I think for one day or so, the next day maybe even still can work out. So just like here for the tap, for the dispensing device, just like something where you can then put the bottles and fill them, bring them home. Yes, works all. But here we then go, of course, a bit more advanced. For example, here there's more machines, but filling system for small industrial filling of gas bottles. You see here, this is a filling carousel. Here the closing machine, and also, as I said, that this is something else. This was made for us where we did not, our can filler was not there, but we already had a seamer. So we made some things where we are just, we're tapping there the beer with a dispensing machine. And then we see like our standalone seamer. Just one moment. Yes, but I remember that also during the pandemic, there were some bars who also had that machine where they could close where they could close a can, and then we're selling beer cans like this for immediate consumption. But here, okay, no bubble breaker, no sublit gas stations, just for immediate drinking. But this is suck. Now it's seamed, and then you can have it for quick consumption, yeah? But here, yes, as I said, like the big companies in this Innofill, the KHS, they of course are also now aiming for the smaller market, but 1,000 to 540 is not really small. But of course, this is already like industrial scale, but there are also even some smaller machines even made by the big suppliers such as Krones, Sidel, KHS. Yeah, craft-made can filler, perfection is small size, 4,800 to 15,000 cans. And here are some advertisement in that USA American beer American magazines. But here is, I think this is like really like a can line, a small can line. We have that thing with a candy pelletizer. We have the grinzer. We have here the filler, the seamer, and looks quite professional. Unfortunately, never saw that in real life. Different speed, 35 to 65 or 35 or 65 cans per minute. So times 60, yes. And so we have, but it's a filling can line for a small scale. Here also 900 to 300 cans per minute, pick up less than 30 ppb of dissolved oxygen, but not just the pickup, not then the headspace. But you see that there are advertising then filling system for also like a can filling lines for 1,200 cans. Okay, this maybe later some more, but we don't have so much time anymore. Just about pasteurization and thermal stabilization, microbiological stabilization. Yes, we have, I think we have some methods for improving the microbiological stability using thermal heat or using thermal methods, the tunnel pasteurizer, the flash pasteurizer, hot filling, and then we have sterile filtration, and I don't know, some other, I don't want to know about that, high pressure things. It is, let's make it say for beer, we usually have the tunnel pasteurizer and the flash pasteurizer. Yeah, hot filling, it's not possible because we were talking about the filling pressure, and if I fill very hot in a temperature which is reducing the germs, for example 60 degrees, I would be so high, have to be so high in the filling pressure that would not work out. Sterile filtration, I know one big brewery in Germany who does that, but usually you use tunnel pasteurizer or flash pasteurizer. Okay, the aims of thermal pasteurization is of course to reduce the germs, but I'm just aiming about the product spoiling microorganisms. So it's not a sterilization. I don't kill everything. I just kill what is necessary to kill, and therefore I want to have no influence or minimum influence on sensory properties, and also of course I want to have low energy consumptions. Okay, I should be low in the TPO because due to that pasteurization, I catalyze my oxidation agent processes. And I need a certain headspace. We had it in the beginning due to volume expansion, and no pathogen microorganisms should be able to grow. Otherwise, I would then have, of course, different requirements. Okay, when I pasteurize, I usually have as a meter the pasteurization units, and I don't know this, but for each beverage needs or even each beer type, you usually needs special pasteurization units. So it's like the intensity of the pasteurization, and what you need is defined by the beverage, by the initial bacteria count, and also the heat resistant of the relevant microorganisms. Here are some overview about usually applied pasteurization units for the specific beer type. So when we have beer, I think it's a bit like just cut that beer and put their lager. This is like a special lager beer. We are between 15 and 25 PU and using 60 degrees. Other beer, for example, wheat beer, we are much higher, a bit higher, and also alcohol-free beer, we are higher than for beer, because of course the alcohol acts also as a barrier for a lot of microorganisms. What is a PU? 1 PU is the time times 1.393 to the power of temperature minus 60. We are talking about beer, yeah? If I have juice, I have other references, but we can skip this for now. We are having a cut-off temperature of 60 degrees. We just start to count beer pasteurization from 60 degrees on. If I would put here now 60, which means T, 60 minus 60 is 0. Any number to the power of 0 is 1, meaning 1 PU is 1 minute at 60 degrees. Yeah? We have here a calculation. We want 20 PU with 60 degrees. We have our formula. Put it here inside. Then we solve that everything. 20 like T by 1, and T is 20 minutes. This is the normal pasteurization time in the tunnel pasteurizer. If I want to now have 20 PU with 72 degrees, and I put that into that equation, I'm ending up with 22 seconds. And this is normally what I do in the flash pasteurizer. Just the comparison, actually, the comparison of the tunnel or chamber pasteurizer and the flash pasteurizer. I think the advantages of the ones are the disadvantages of the other. The main advantage of the tunnel pasteurizer, the chamber test pasteurizer, is that I pasteurize the filled beer in a can or in a bottle, and therefore I pasteurize also the packaging material, and it's closed. There is no recontamination necessary possible. So it's a more safe method. Yeah. With the flash pasteurizer, there's a recontamination possible. It's only possible when I have really safe and clean environment. Yeah. Usually in Germany, we do the flash pasteurizer when we have when we use returnable bottles, because we know that they are very clean, coming very sterile, not sterile, but more or less sterile from the bottle cleaning machine. When we are filling cans, we usually use then the tunnel or chamber pasteurizer. But of course, the flat tunnel pasteurizer, much more, very big machine, investment costs, you need space, and you have higher thermal consumption and a higher thermal load for the product. The flash pasteurizer is basically, it's a heat exchanger, nothing else. So it doesn't need energy. That does need energy, yes, but it doesn't need space. It doesn't need. It's just a more or less inline thing, yeah. And we have also low thermal influence for the product. This is a batch pasteurizer. For batch operation, they are different size. Actually, you have there, you put there the bottles, and then you apply heat. In this case with steam. This has, for example, 500 bottles. You then have monitor it. You put there, here's the cold spot, the coldest part, because of course you have to ensure that even at the coldest part, there was that heat treatment. And yes, and there then exist in that batch pasteurizer, the chamber pasteurizer, also in different sizes. For example, this one fits 12 pellets, quite big actually. But then inline, and we have that inline machines, that is a tunnel pasteurizer. The slow transport on the container through the pasteurizer, and then we have water sprayings, showers actually, with first increasing heat and then afterwards decreasing heats. For bottles, glass bottles, more important that stepwise than for cans, but you also usually have that also with the cans, because you can use then some recuperation effects to reduce thermal energy. Yes. And then there is that pasteurization temperature. Once it reaches at 60 degrees and then held constant during pasteurization, and then afterwards is cooled down again. The throughput time you see here, yes, with glass bottles slightly higher than with cans. They are out of stainless steel, which should be able to stand some chloride, actually also for disinfection, because we need to disinfect here the bars, because in case of breakages, we have product, we have here heated up, so we would have some water bars which allowed 30 degrees, and then with product residues can be, of course, a very good climate for microorganisms. Okay, maybe just short now here to the recuperations. We have here the infeed, here the discharge. And we have here like we have a warm water bar storage, hot water storage, cold water storage, and somehow with this storages, the water is somehow brought to a temperature that we have then water in the different desired temperatures. So we have here warm water, warm water, warm water, and then pasteurization, 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 and then cold water, cold water, cold water. What I wanted to show in this sketch, if I now here are at warm water storage 3, actually, I said the bottles comes from shower, they are heated up by showers. And here is that shower, and if you go back, that shower comes from this cold water 3. Here the water has 49.9 degrees. Then it goes here and showers the bottles. These are the bottles to heat up. So the bottles then are heated up, and therefore the water cools down, in this example, to 47.3 degrees. And this water then of this warm water zone is used then here to cool down the bottles. So the bottles are cooling down, the water warms up, and so on. And you see here we have this communications with all of those warm water and cold water, yeah? That you always use the water from this one would use here the first, and so on and so on. And this is how to have like the energy consumption as less as possible. You see here in this case, so this is here the pump, for example, and this for the bus, and this goes here to that shower, and so on and so on. Actually, this is from the backside, the pasteurizer, where you can see here the water distribution, and so on and so on. Yeah, this is how it is done. Here you now see the warm water. Actually, this is the temperature inside the water bases. Yes, warm water, pasteurization, cold water, as shown in this thing. And here you see the temperature in the bottle. And of course, it's a bit with a delay. However, then we are reaching here somehow then the pasteurization temperature. And here in this case, when it reaches then the 60 degrees, we're starting to count the pasteurization units until here, and then the pasteurization units are calculated, and then we know that we have the stable product. Consumption data here. Let's maybe, I think, of course, it's a bit now old. I'm sorry for that, but just we can keep that in mind because we will compare that now to the flash pasteurizer. But you see here for 30 cents to €1.35 per hectoliter, the consumption data of the tunnel pasteurizer. Yeah. So now just shortly to the flash pasteurizer. As I said, it's basically a plate heat exchanger where we have the beer. Here actually it's we have here the steam, and here we have the hot water unit. So, but now we have then here the beer flow. Here is that booster pump. It's very important to increase the pressure that to increase the pressure because we're heating the beer, and therefore due to the CO2, it is the pressure is increased, of course. And then we have here like then our the product way, and then have for a certain time 30 to 60 degrees until here we have then also some recuperation. Here the cold beer is going in, and then of course it's here then preheated by the beer after the thermal process, and so on and so on. It's also kind of like we have that recuperation, and in the end we cool it down with fresh water. or we can use for this because it doesn't have any product content, maybe some water we were collecting somewhere else. There are very intelligent energy concepts often. In the end, the beer goes out with 70 to 12 degrees, but had then here his time about 30 to 70, 30 to 60 seconds, about 70 degrees. We can skip this. What I wanted to see here, we are now with 7 cents to 20 cents per hectoliter. Of course, much lower with a consumption as a tunnel pasteurizer. So if my hygienic situation is allowing me to use a flash pasteurizer, of course it is advantage concerning the money and also like the impact on the product. Okay, kegs we still have. I have some, yeah. Okay, so like here, I think this is maybe relevant for historical thing or as a gimmick, but that old casks, I think they're not state of the art anymore. You have here like, okay, this have a steel cask, and then maybe you have a plastic mantle, you have a tap hole, a bung hole, and another tap hole for that Bavarian thing. Of course, they also exist from wood. Here is more or less like a historic filling station for cask, but however, it is more or less if it's done, no, we'll see now it's later on quite not modern way to use that. But I think that cask, I don't know, it's for really like a traditional thing. For example, in Cologne for their Kölsch, and therefore also in Düsseldorf for their Altbier, they like to have those things, and therefore it's still the thing. But usually you don't have that anymore in industry, also craft beer or so on. But here you have then, of course, actually like you would fill a bottle, you pressurize it, and then you fill due to that thing here, and then afterwards you remove it, and then you have to be quite fast to put there the thing to close the tap. But as I said here, for example, this is Düsseldorf Altbier, where this could be done modern. Nobody has to hold their keg anymore. Or some make something by hand. You have here the thing. Here, then this is a filler. The beer is now filled. It goes here. Then you see here. Eventually, then there is an overfoaming that guy has something like a mechanic, like a pistol, to put there the closer, and then the can is ready. Here the next can comes. So even for those with very traditional ways where those still are the casks are a thing, you can make it quite modern in these times. However, I don't know, there exist those Cornelius kegs, soda kegs, somehow where you have like the way for the gas separately from the product way. Sometimes it's often used, especially for craft brewer, because they have the big advantage that you can open them manually. But I think that kegs now, in this case now, the stainless kegs are very state of the art. So they are like, they have, of course, the keg itself, which is like stainless steel or sometimes with a plastic coating. Then we have a spare and the fitting. The fitting is important then together with because it is the connections either to the gas phase or to the product phase, and together then with a coupler, you can open and close the way so that you can get the gas in to get the beer out. But this is state of the art. They exist in different shapes. Returnable keg, so you see here Euro keg, standard keg, slim keg. Important is that you have the coupler, which is the one you need, yeah. Sometimes often so that slim ones often used, for example, for soft drinks, because often they have a bigger product variety, and then you have for the same space, ground space, you can have different, you can have more products. Here's some suppliers just to name some. Also nowadays quite popular, especially also for small breweries and for export. And if you can afford to have a keg pool, are those one-way kegs. Yes, sometimes, of course, first of all, you think it must be very bad for means of sustainability. However, if you can send your keg from one part of the world to another, maybe it is then even the more sustainable way. Of course, somebody who's producing stainless steel kegs will always show you numbers that stainless steel is more sustainable. Somebody who produces those will always say this is the way to. However, you should see that for our experience, we made often with those, not with all, but let me say with the big suppliers. I don't name them, but I think you maybe know which 3 of them I know. We made some research and we can say, like, sensory-wise, within their shelf life, they perform as good as a stainless steel. Yeah. So they have, of course, they have some oxygen scavengers. This one has the beer in a aluminium bag. So within that shelf life, they're performing very good. So maybe sometimes even also, like, I don't know, in times of the peaks, summer or so, maybe this is a way to also then use more or less. They can be used within the normal equipment. So could be always a good alternative, I would say. When using those kegs, please consider there is a danger because they are pressurized and to, I don't know, up to 3 bar, what you are allowed to use for taking. And when they are empty, pressurized, and then you pierce them, it is going to very dangerous big. We also made there some things they are flying, I don't know, 20 meters up and can be very, very dangerous. So always release the pressure before then open or cut them down for dumping them. Yeah, but all of them has some devices to depressurize them. Yeah, this one, for example, has at the coupler some pressure release. This is very important. Okay, here are the different couplers. I don't know what is in Sweden the way, but we in Germany nowadays often have that, like to have that that flat. It's good for micro, but for example, then there is like that S, that Sankey, which is, I think, very common in USA. However, you just need the right one, and then you can use. This is what I said, that Corny keg, that Cornelius keg, soft drinks keg, where I don't have, like, with that fitting the gas and the product the same. I have here gas and here product, or vice versa, I don't know. And this one I can use easily. Yes, here are those dispensing heads, couplers. I don't know, you know which one you need. Okay, then to the fillings of kegs. Filling and cleaning of kegs is done in the same machine usually, and it's done, can also be like, this is like here with 2 filling and cleaning stations. Here 35 to 60 kegs per hour, 60 to 600 kegs per hour, and here like more than 600 kegs per hour in a rotating thing. So it is. However, what is your requirement? You can make it quite big. Okay, to the different steps of cleaning and filling a keg. Station 1, centric at the infeed. So, and now we come already with the very important step, the pressure control. Yeah, this is the first thing. If I want to clean and fill a keg, I have to check if there is pressure on. The keg is filled with pressure, with CO2 usually. So when I give it back to the brewery, it should be pressurized still. If it's not pressurized, it might have been opened. And if it might have been opened, somebody could have done the very, very bad thing. For example, putting oil or whatever. So every keg which is not pressurized anymore, I have to take out and make a pressure make a further control, but it doesn't go to the normal product pressure. Yeah. So what then is done is the replacement of residues and CO2 with sterile air. So first I go air. You see here I have here my the product way, and here is the gas way, but I have it upside down, and go now with sterile air here to the product way, and then to remove residues. Water rinsing steps, the same, always going in with the product, out with the gas. Then water out, displacement of rinsing water with sterile air. And then I start the cleaning with hot caustic. And I make it pulsating. I make it with high pressure and with low pressure. With high pressure to reach the outer inner surfaces, with low pressure to release that spear, to reach that spear. This is the first step of cleaning. So I take out that caustic with sterile air, and then I have a second pulsating caustic rinsing of the inner surface and spear. So I do that 2 times. Then I fill with caustic to a certain level. Important, it's also one reason why it's upside down, is that I have here where those areas, yes, where more gaps and more other things, microorganisms and so dirt can more easily here, and those parts than up here. This is why I have it then here filled with caustic for some time. For example, 150 seconds for wheat beer, where I might have more organic dirt. Soaking of the spear and filling with caustic parallel, then I can also make that pulsating and surface pumping, caustic pumping to have the cleaning. If this is done, here's another third pulsating step. I remove that caustic with sterile air. Now, water rinsing, and now I have an acid step. Acid, usually I don't use hot, it's always cold, and I make it also to, I don't know, remove maybe some things which inorganic stuff which could not be done by the caustic, but also to neutralize possible caustic. Caustic out, hot water rinsing, and then very important, steam. Yeah, I put the hot steam, and with the steam I cannot watch in the keg, so this is why I need the steam to be very short. The steam is reaching everything. No microorganism would be able to survive that steam. So I steam the keg with 1 to 2.5 bar over pressure, 120 to 135 degrees. So then the steam is keg, and now everything was before with sterile air. Sterile air usually you don't use in the brewery, but now it's this that we also don't use the CO2 anymore. We then displace with CO2, because in the next step we pressurize just like a bottle, and then we start filling. And in this case, we are now starting the filling from the gas way, which is usually the gas way, because then we fill it from upside down until the keg is filled. Yeah, that's it. Here, can you see this is a plastic cap? Like we can see, that is also nice of them that you can see somehow what happening. But here you see now the keg here is filled with beer at a certain speed. Usually also those kegs come, when you get them here, they are coming pre-pressurized. Okay. Yes. And so we have the keg full of beer, and the people in the bar can enjoy. Yes, we very easy way to check if the keg right is right to use the scale. Here this are some pelletizing, depelletizing of those soft drink cap. I think it's then here done with this robot. Yeah. Yeah, this is a quite modern way. I think it's not now relevant for all of us, but you think more and more, especially that work where you have to lift heavy stuff, it's more and more done by those robots. I think, yes, it's getting time, but just very quickly, the labeling machines. After the filling machine, labeling usually for beer bottles, glass bottles, the usually way is to have that wet cold labeling. Traditionally or always done with casein as a adhesant, was working very good. However, it's not vegan, and therefore more, not only this, because also of other things, but one of the reasons more and more synthetic glues are then now in the market. So this is like the wet gluing. You have is there a picture of the machine? No, we'll see maybe later on. Okay, but we have those rollers also. And here, this is the glue roller. Actually, yeah, as I said, it's a big roll, and it's like with that wet glue permanently floating with that glue. So we have always here a layer of glue. The first step is that that gluing pellet goes here at that station and takes the glue. Yeah. So this thing is now full of glue. That pellet. I think we have here. Yes, this is the gluing pellet and goes that, and this thing is then full of glue. It's a slam, the lamelle, and then the second step is here is a label supply, comes from the label box. They're all stepped together. And then this pellet with the glue goes here and takes the label. You see here, this is the front side of the label. Next step is there's that gripping cylinder here, where then the labels are transferred, here gripped and transferred. This are now at those grippers. And then next step, the bottle comes, label goes to the bottle. Due to the glue, it stays there. And then the last step is then with those brushes that the labels are attached to the bottles. Maybe this is something also interesting for small breweries, for craft brewers, those self-attested labels, actually like a sticker. When often this is some where like anger of the breweries that when the small brewery, when they're using those pool bottles, which are used for several breweries, and then they are putting stickers. With the normal bottle cleaning machine, there will not be, you cannot use them. So if they have that for returnables, it has to be like, of course, you need a special cleaning agent, which are used for that, but often they're also used for one-way bottles. Yes, of course, they have to be dry. And then is it here, you see here somehow those, doesn't work the video, but you see however this is then implemented, but also, of course, it is much easier or the machine is much easier because you always have already the glue on the stick, and then you see here's the label, and then here it is good. It is put to the bottle, and then here to that guiding rail, it is then glued fixed. This is. I don't know. Actually, this was a video. Oh, yeah. Here, like a semi-automatic machine, the bottles are still put manually, but then you can see how it is here then done also in a very small scale. That you have here the labels on this, and then they are applied to the bottle. So that is something with itself, a taste of label that you can also there, especially for small breweries, it could be interesting. I don't know, 10 years ago, it started with those direct printed on the container of course, you can buy it at the manufacturer already direct printed, but this should be, or what should be, I don't know, it was, I think, not so big nowadays, but that you have machines which are printing direct the label on the bottles. But I never saw that in real life, only in presentations and at some trade fairs and so on. Okay, so that was it. I hope I met your expectations.
Thank you very much. Very interesting and very good.
Okay, so you have here actually, this is the contact of a colleague, but you also have my contact in case you have more questions. Just write me. We are there for you. Also go over Jan Biering and so on. We are happy to answer questions. I don't know if you have now questions. Otherwise, I would say just contact us. Okay.
Yeah, thank you very much. Thank you.
Thank you too very much. See you.
Thank you very much.
That's great. I just gonna talk
Thank
to
you.
the students now, so thank you very much. Great.
Okay,
Bra. Jag bara tänkte jag skulle visa. Can you stop sharing? Sharing, not sharing. Sharing. Yeah, thank you. I just gonna talk
yes,
about a quick.
I want to go out actually.
Yeah.
Yeah. I just.
It's no problem.
It stopped. Just go out of the meeting.
Yeah, you can
go out of the meeting. Okay,
yes,
bye bye.
Bye bye. Jag vill bara visa en sak här. Nu ska vi se vad jag hade den där. Vi har ju dragit över som fan. Vänta, vad fan.
Nej, men vi började ju senare. Vi har inte dragit över.
Det är bara att
Han höll tiden precis. Nästan.
Ja, verkligen. Det var ju mitt fel att jag hade helt missat.
Det var jättebra tycker jag.
Ja, jättekul alltså. Jag vill bara visa det här. Det var det här. Det du pratar om. Ser ni min skärm? Ja. Alltså bara så här på examensarbete så har jag gjort i ordning här. Om man trycker på den här examensarbete-filen, då ligger allting här. Examensarbetemallen som är väldigt välskriven. Här kan man spara examensarbete. Eller förlåt, det står ju här sparar ifall du vill diskutera någonting med mig så kan du lägga den där. Och då kan vi ju jobba på den båda två liksom. Och sen finns det slutgiltig inlämning av examensarbete som en punkt här där man pumpar upp den. Ser du det?
Ja, men jag tittade på kalender för jag var nyfiken på vilket datum som gällde. Men då är det 20 december som är innan.
Ja, egentligen jag måste ju hinna rätta också så en vecka innan där.
Okej.
Ja, det ska jag skriva tydligt. För jag måste ju hinna läsa igenom och rätta också. Men redovisningen är den 20 där runt omkring. Det var bara det. Men då finns ju allting här sen. Så det vet ni. Bra! Tack för idag. Nu måste jag slänga mig på cykeln. Jag ska in till mitt nästa här och sjunga lite grann. Så att jag ska stänga av den där.